Okay, so where are we? Okay, so is there a unique solution at the point 0, 1? Well, here's our differential equation, right? So we need to test this, right? You don't put values into the solution. Everything that method, that's not going to work. Okay, you have to do these two tests, and the test where it fails, if I take the partial, this is my function, right? If I take the partial derivative of f with respect to y, I get this, and y cannot be equal to y cannot be greater than 1, right? Excuse me, y cannot be equal to 1, right? So if y is equal to 1, you're not going to have a unique solution. All right, so you do not have a unique solution. Y is equal to 1, and by a unique solution, it turns out that as I've shown here, these are four ways of expressing y in terms of sine and cosine produce the same curve. It turns out that y equals 1 is a solution to the differential equation, right? And also, we determined that this is a solution to the differential equation, and y equals 1 is a solution. Put y equals 1 into this differential equation, you'll see you get a solution. So you actually have two solutions, right? When you have two solutions, you do not have a unique solution. So so a unique solution does not exist through the point y is equal to 1. All right. But see, all you had to do is you had to just do this test. The partial of y with respect to f tells you that you cannot be equal to 1. All right. And sure enough, there are two solutions. The solution you found in y is equal to 1 is also a solution. You put y is equal to 1 here, you'll see. Okay. This is 0, right? And then the derivative of y with respect to x is 0. So you don't have a unique solution. Okay. Mostly everybody got this right. So this was just simple separation of variables and putting in the initial condition. So you can compare, there's different ways of writing this. You can write this as 3/2. I know some people also wrote it in terms of cotangent. That's fine. Okay, most people got this one right. There's a couple of people that don't know how to do a method of, you can't separate this. This is a differential equation you can't separate, so you have to use a method of an integrating factor. Okay, so there's a couple of people that you will get on the final exam, you will get a problem where you have to solve a differential equation using an integrating or integration factor. Okay, and then the largest interval, well, this is valid between minus infinity to infinity. Okay, now this is, I think I just took off 1 point. This was worth 2 points, but I took off 1 point. The transit term, a lot of people gave me the transit term as being c e to the minus t squared. That's not fully correct, okay? So if you gave me that, I should have just taken off a 0.5 point. But the transit term is the full thing. Now, you need to understand this, okay? I could write this, right? I could write this as also as c, right? E to the t times e to the minus t squared, right? Now, when minus t squared goes to 0, you're multiplying this e to the t, so that's going to go to 0. So this whole thing goes to 0. So if you excluded this t, and I guess when I start writing, maybe I'll show you what I mean if you're having trouble with this. But because when we get into spring mass systems, we're going to be looking at terms that are transit and terms that are steady state, and you need to understand it's the full term that's going to go to 0. Okay. Most people got this right. Okay, I gave you the script, right? You just had to copy the script in. You did. Oh, the other thing is that you denote. If you don't have to solve the differential equation, right? If I don't tell you to solve the differential equation, you don't have to solve it. So in this problem here, I know some people actually tried to solve the differential equation. This is a nonlinear differential equation. You can't solve it, but you didn't need to solve it. Okay, the directions say use MATLAB to generate the direction field for the autonomous differential equation, right? and then print out the direction field. And these are possible solutions, right? That's what's showing here. These are possible solutions. So this is a graphical interpretation of the solution. You did not have to try to solve the differential equation. Okay, a couple, and what should I the so if you try to solve it, I mentioned that you need to. Okay, I think everybody, with the exception of one person, got the Euler's method problem right, and I think one person had the number was off, but it appeared to me they knew exactly what to do, and so I think I didn't take off any points. Like instead of 5.3, they had something like 5 point. I don't remember, but the number was off somewhat. But there's one person that didn't have a clue on how to solve this this differential the Euler's method. Okay, and this, most people got this right. All right, so once again, take a look at your exam. Take a look at my comments. If you think I made a mistake, I once had a student come to me with a mistake that I forgot to subtract a point. I think I gave the student 100 and he deserved a 98. It was one of these students that got 100 on every exam anyway. And I think this was like the third exam. So, okay. All right. So, you go into my grades, right? If you go into my grades, you could see your, yeah, you could see your, someone have something in chat. Okay. Actually, it's better just if you want to record, it's actually better just to call out, because I'm not looking at the chat while I'm trying to teach. Okay, so let's see. All right, so what I want to do now, let's see. I'm actually going to be right now. I'm going to be talking to view graphs, but then I'm going to move towards writing stuff out when we get into solving problems. Okay. So now we're going into week 3, and we're going to look at the preliminary theory of linear equations. Okay.
Can I get permission to record? Sorry for interrupting.
Yeah, okay. Let's see here now. Okay, who am I speaking to now?
Philip.
Okay.
Philip Asiama.
Okay. All right. Okay, so let's see. This is not what I want to do here. Okay, so I'm gonna. Does everyone see the view graph that says preliminary?
Yes, we can see it.
Before we start, I have a quick question.
Sure.
The grade that's put into Blackboard, it's out of 100, right?
Yes.
Okay.
Right. Now you'll see a grade and then like a 15 underneath it. That means it's 15% of your total grade. Okay, because yeah, it's 15% of the course grade. But yeah, the what you got on this test is the top number. But I think Blackboard shows a number underneath it too. Okay, and you should be able to bring up your exam and look at what I marked wrong. Okay, so this stuff here, what's the right way of phrasing this? It sounds a lot more complicated than it is. Believe it or not, it's very simple, but we're required to talk about the preliminary theory of linear equations. When we actually solve equations, this stuff is going to become pretty straightforward. So just keep that in mind. All right, so first of all, we have an nth order homogeneous linear difference. Now, homogeneous means that this is equal to 0, okay? So here's an nth order. As you see, it's linear, right? This is linear because we have functions of x in front of all the derivatives. So this is, and also y, so it's linear. When it's homogeneous, some people pronounce it as homogeneous. When it's homogeneous, it's equal to 0. When it's non-homogeneous, it's we also have that this could be equal to some function. And here we're calling the function g of x. Okay. Now, basically, the basic idea here is that we can add solutions together. And we could add solutions together with any constants in front of them. That's the basic concept. Okay. And so if we have solutions, say y1, y2, y3, y to the n, where we have an n order differential equation, then any linear combination is also a solution. Okay. So for example, if I had a fourth order differential equation, all right, then C1 times Y1 and C2 times Y2 and C2 times Y3, that would be a solution. So any linear combination would be a solution. All right. If I had a fifth order differential equation, well, this will be a solution plus any linear combinations of these. So, it's just kind of what we talked about initially too, that if you have a first order differential equation, you're going to have one constant. If you have a second order differential equation, you have two constants, right? And so this is called the principle of superposition. You might have heard it before, like in physics, when you calculate the electric field, if you have a number of point charges, right, you use the principle of superposition. All right. All right. So as far as the preliminary theory of linear equations, we're first going to consider an nth order homogeneous differential equation. So once again, an nth order homogeneous differential equation is when this is equal to 0. All right. And here's examples. The examples, I think, make it pretty clear that, okay, so here's a third order differential equation. All right. This is a third order differential equation, and possible solutions. Two possible solutions is x squared, there may be others, and x squared times the log of x, right? If you plug these in here, you'll see that these are two possible solutions to this differential equation. So if these are two possible solutions, all we're saying is that any of these are also a solution. In other words, C1 times x squared would be a solution. C2 times x squared times the natural log of x is a solution. And C1 times x squared times C2 times x squared natural log of x is a solution. So that's all we're saying, that if you have solutions to a differential equation, we're going to call these the fundamental solutions, that any linear combination is a solution, right? So here's another example. This is a second order differential equation. Now, you don't know how to solve these yet. Okay, that's actually, I'm hoping we're going to get today how to solve this type of differential equation. But this differential equation has two solutions, right? One solution is the cosine of 8x, and another solution is the sine of 8x, right? So therefore, what we're saying is that any of these are also a solution to the differential equation. In other words, C1 times the cosine of 8x, C2 times the sine of 8x, and C1 times the cosine of Cx. And the boundary conditions are going to determine, the boundary conditions or initial conditions will determine whether we have, what the C values are. Okay. Now, okay, let's see the next one. Okay, now, the important thing, though, let me just go here for a minute, is that these solutions are linear independent. In other words, there's no way I could have, I could make the sine a cosine. I mean, a sine is the shift of a cosine, but I can't multiply by a constant from cosine to get sine. So cosine and sine are linear independent. And these functions here are linear independent. In other words, x squared, I can't get x squared natural log of x by multiplying this by a constant. Okay. So the important thing too is that when you have solutions, like if you have a second order differential equation and you have two solutions, that the solutions are linear independent. Okay. One cannot be written as a linear combination of the other. And I think the best way of understanding this is with an example. Okay. So, so first of all, if you have a set of functions that are said to be linear independent on some interval, that there exist constants not all equal to 0 such that this equals 0. All right. Now, like I said, I think the best way to look at this is with an example. So here's an example to best illustrate. So consider these 4 functions, right? I got these four functions. One is square root of x plus 5, square root of x plus 5x, x minus 1, and x squared. These functions are actually linear dependent. Now, the reason why they're linear dependent is because this middle function here can be written as a linear combination of 1, 2, and 3, right? See, they're not all 0. In other words, I can write f2 as 1 times f1 and 5 times f2, right? See, if I multiply 1 times f1, this is f1. And if I multiply 5 times f2, and then 0 times x squared, I end up getting f2. So this is an example of functions that are non-linear dependent. Okay. I mean, these are functions that are linear dependent, right? We want functions that are non-linear dependent. Okay. Now, a way of testing, and we're doing this without proof, a way of testing whether functions are linear dependent or independent is what's called the Wronskian. And this is very simple, that if these are different functions, right? And let's say you have an nth order differential equation. Let's just say, for example, that we have a second order differential equation, right? That as all as I have to do is find f1 and then f1 prime and f2 and f2 prime, and then take the determinant of this. Okay. So let's see. I thought I had it on the next one. And if the determinant, I guess I did it here. All right. If the determinant's not equal to 0, then they're linear dependent. If the determinant's equal to 0, then they're linear dependent. All right. We'll go through an example. So so the thing is, if you have a third order differential equation, you can have a 3x3 determinant. If you have a second order differential equation, you have a 2x2 determinant that you have to calculate. All right, so let's see. So okay, so this is basically what we're saying now. Now that we introduced the Wronskian, that if we let y1, y2, y3, y to the n, we're doing this for n, be n solutions to the homogeneous linear nth order differential equation, right? These are the solutions to the nth order differential equation on some interval I. Then the set of linear independent, then the solution to the set of linear independent I, if and only if. In other words, these are going to be linear independent if and only if the Wronskian is not equal to 0. Now, I actually didn't give you any problems calculating the Wronskian doing this. When we actually solve differential equations, you'll see how this all works out. And when we solve, and we're going to focus on second order differential equations, okay? So, okay. So once again, if we just had a second order differential equation, we just have y1 and y2, right? If we had a third order, we'd have y1, y2, and y3. Okay. All right. So this is just telling us that, this is what I just did. Yeah. That we call this a fundamental set. In other words, the y1, y2, y3 of the n linear independent solutions of the homogeneous nth order differential equation on interval I is said to be the fundamental set of the solutions, right? So this is the fundamental set, and any linear combination, all right? Each one of these are linear independent, right? But any linear combination is also a solution, all right? They're linear independent, but linear combinations give you a solution, okay? So these are out of your book. These theorems are out of your book. So if you wanted to read a lot more about this, but the book could be pretty. The book is good, but it could be pretty. They spend a long time getting right down to what's important. Okay. So once again, now the existence of a fundamental set. So there exists a fundamental set of a solutions for a homogeneous nth order linear differential equation on some interval I, then the general solution, right, can be written as any linear combinations. Okay, so once again, so here's a fundamental set, and I guess an example will make this clear. This is our fundamental set of solutions of the homogeneous nth order differential equation on some interval I. So these are differential equations. So a general solution would be C1, Y1, C2, Y2, up to the order of the differential equation, where the C's are arbitrary constants, right? The constants are determined by initial conditions or boundary conditions, right? So here's an example, all right? So the solution to this differential equation, well, first of all, the interval is from minus infinity to infinity. It could be some interval, but nevertheless, it has to be some interval. And that, I know we don't know how to solve this yet, but hopefully we're going to learn how to solve this differential equation today. Hope to get to that. That the solutions to this differential equation, or the fundamental set, is e to the 3x, and y is equal to e to the minus 3x, right? So this is the general solution, right? This is the general solution, right? Any constant C1 times Y1, any constant C2 times Y2. Some of this is what we already learned, right? Now, if I calculate the Wronskian, right? The Wronskian, this is Y1, and then this is the derivative of Y1, right? This is Y2, right? This is Y2, and then this is the derivative of Y2. And when you calculate the determinant, right? If I multiply this times this, I get minus 3. This times this, I get minus 3, right? Everybody knows how to take the determinant. So then this is minus 6, which is not equal to 0. So this is actually telling us that these are two linear dependent solutions, all right? So here's another example where the solution to this differential equation are cosine of 6t. Solution to this differential equation is sine of 6t. So that's the fundamental set. So then any linear combination is a solution to this differential equation. So this would be the general solution. And then if I was to calculate the Wronskian, I could see that it's not equal to 0, right? This is x1, right? And then this is x1 prime, right? This is the derivative, right? This is this is x2, and then the derivative of x2 is in this case here, it's 6 times the cosine. Then if I take the determinant of this, right, it's this times this minus this times this, so I get 6 times cosine squared plus 6 sine squared, and so that's equal to 6, so it's not equal to 0. So this is showing us that we got that these two solutions are linear dependent, and any linear combination is a general solution. Okay. All right. So now we're going to talk about a non-homogeneous differential equation. Okay. So a non-homogeneous differential equation, this is not equal to 0, right? We write it in this form, and when it's non-homogeneous, we also have some function of x, right, which I'm calling g of x. So this is not equal to 0 for a non-homogeneous differential equation. All right. Now, any function, right, y of p, free of arbitrary parameters. Now, we'll see that when we look at the solution to the differential equation, there's arbitrary parameters, but it turns out the particular solution is not going to have arbitrary parameters. You'll see this in a minute. So y of p, free of arbitrary parameters, that satisfies the differential equation is said to be the particular solution of the differential equation. So that's why we write the y of p, okay? So y of p, all right, y of p is a function that when I plug it into this differential equation, I get both sides equal, all right? And it's not going to have any parameters. It'll be free of parameters, all right? Okay. Well, free of arbitrary parameters. Yeah. Okay. Okay, so if we let y of p be a particular solution to the non-homogeneous nth order differential equation on some interval, and y1, y2, y3 be the fundamental set of the associated homogeneous linear differential equations, then as all we're saying is that the solution to this differential equation, I should have made this clear, the solution to 2, right, is just the sum, right? This is telling us that we add. It's a linear combination. In other words, the solution to the non-homogeneous differential equation is the solution to the homogeneous differential equation, right? The y1, the y2, the y up to the y to the n, plus the particular solution, right? So this here, this is the total solution. Let's see on the next chart. Okay, so the general solution of a non-homogeneous differential equation consists of the sum of two functions. It consists of the linear, the linear combination, which is the general solution of the non-homogeneous differential equation. And we call that the complementary function, right? That's called the complementary function. That's why, yeah, we call that the complementary function. That's why we put the C here. That's why I put the C here. It's called the complementary function. So all this, so the C1, Y1, C2, Y2, so on for an nth order differential equation. I can call that all YC, which is the complementary function. And then Y sub P is the particular function, is the particular solution. Okay. So the complete solution is the sum of the two. So let's see. So I think here on the next chart. Okay. So Y, or the total solution, is the complementary function plus any particular solution. So in other words, to solve a non-homogeneous little differential equation, and this is what we're going to be doing some non-homogeneous today, I heard. We first solve the associated homogeneous differential equation, and then we find any particular solution to the non-homogeneous. All right. So that's the order in which we have to do it. And you'll see why. So we always have to solve the complementary first. And the reason why we have to solve the complementary first is because there's certain things that we have to do to make sure that our particular solution is linear independent from the complementary solution. Remember, all these, when we have a solution to the differential equation, right, all these y1, they all have to be linear independent from one another. And the yp also has to be linear independent. Okay. All right. So here's an example. Now, if you understand the example, that's what's important. All right. All the mumbo jumbo that's in the book is understand the example. So here we have a differential equation, right? It turns out the complement, in other words, if I set this equal to 0, the solution to this differential equation is just this. Okay, so this is the complementary function, right? It turns out that the particular solution to this differential equation is this. All right, this is the particular solution. All right. Then the total solution is the complementary solution plus the particular solution. Okay, that's all we're saying. All right. So once again, this is the solution. This y sub c is the solution when this is equal to 0. All right. We find that first, and then we find the particular solution. Right. If you were to plug this into here, if you plug this particular solution into this, you're going to see that you'll end up getting x squared on both sides. And we'll learn how to find a particular solution, and we'll learn how to find the complementary solution. But right now is all we're saying that the total solution is the sum of the two. That's all we're saying right now. Total solution is the sum of the two. And here's a second example that the solution to this differential equation. Now here, I did this intentionally. So this one here now is cosine of 3x, right? So both of these examples have the same complementary solution, right? Because it's the same. If I set this equal to 0 and I set this equal to 0, right? It's the same differential equation. So this differential equation and this differential equation both have the same complementary solution, right? Hope everybody sees that. but they have different particular solutions, right? The particular solution to this differential equation, if you plug this in here, you'll end up getting cosine of 3x on both sides. But the solution to this, the particular solution is different. But the total solution for this differential equation is C1 cosine of 2x plus C2 sine of 2x minus 1/5 cosine of 3x. So this would be the general solution. And we call it general because we still got these constants C1 and C2, which we, once again, those are determined by either initial conditions or boundary conditions. Okay. All right, let me, I just got 2 more charts. And if you understand the last chart, that's all what's important. Understand the example in the last chart. All right. So now we're just going to go one step further where we're going to say now that, okay, we have a differential equation. We have some function g of x here, right? And, but now we have multiple particular solutions, all right? So in other words, I have a particular solution P, particular solution P2. I have a, excuse me, I have a P1 particular solution, P2 particular solution, up to P to the K, right? And that corresponds to distinct functions, which I'm calling G1, G2, GK, all right? So what that means is that, okay, I can have different particular solutions because I have different different functions of G, that the total particular solution is the sum of the individual solutions. So in other words, like here, I got a G1, G2 up to G to the K, right? Then I can have a particular solution, P1, P2, dot, 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 up to P to the K. All right. When we do problems, this will become clearer. Like I said, it sounds a lot more complicated than what it is. All right, now, understand this problem. Understand what I'm trying to do here, and you got it, okay? All right, so once again, I'm using this as an example. So we got this second order differential equation, and for this differential equation, right? For this differential equation, this is the complementary solution, right? We did that on the previous chart. This is the complementary solution. And this is the particular solution, right? So the total solution is the sum of the complementary and the particular solution. And I'm calling this P1, I'm calling this G1. So this is the general solution. This would be the general solution to this differential equation, right? Now here, once again, this has the same complementary solution, right? This differential equation has the same complementary solution because if I set this equal to 0 and this equal to 0, right? It has the same, both of these are the same homogeneous differential equation. But now I got a different G2 here, right? This is what we did before, previously. I got a different G2 here. But this G2, the particular solution to this G2 is actually 1/5 of the cosine of 3x, all right? So what the previous chart is telling us is that if I have a general solution to a differential equation, which looks like, you know, this here, and now I combine the 2 particular solutions. See, that's what I did here. I got this x squared and I got the cosine of 3x. Here I got the x squared plus cosine of 3x. That the general solution to this differential equation is just the complementary solution plus the 2 particular solutions, right? This is one particular solution, and this is the other particular solution. So in other words, the total solution is the complementary plus particular 1 and particular 2. This is, if you understand this chart, you know, what's going on here, that's really what it's all about. That's really what I want to make sure you understand. That, so before I go on, are there any questions? Basically, it's telling us that we can add, right? We can add stuff, right? I find the solution to this, I find the solution, I find a particular solution to this, I find a particular solution to this. If I now have a problem where the I have the non-homogeneous includes both terms, then the solution includes both the particular solutions I found. Okay. So, you know, if you read the book, it sounds very difficult. And I think the examples make it very easy to understand. Okay. So if there are no questions, what I want to start doing now is how to solve a first order. What we're going to do, we're going to solve first order differential equations with constant coefficients. And then to solve other higher order, like the ones I have here, we'll end up doing power series. Okay, so, all right, so what I want to do now, so now I'm going to go back to writing. Okay, all right. I got to change my, let's see. Okay, now you can follow along on the next section. Let's see. Let me go back to, let's see here. Give me a second here. Okay, so if you go to Blackboard, we're skipping 3.2. If you go to Blackboard and you go to, you can follow along on 4.3, homogeneous linear equations with constant coefficients. Okay, so that's what we're going to start talking about now. Homogeneous linear differential equations with constant coefficients. So the first chart looks like this. All right, but I'm going to write stuff out now. All right, so you can follow along. Okay. So, all right. I think this is a better way of learning. So, okay, so I'm not going to share my screen. I'm writing paper. Believe it or not, differential equations with constant coefficients are easier to solve than equations that we solved before earlier, as long as you know the quadratic equation. Okay, so to solve second order differential equation with constant coefficients, you need to know the quadratic equation. Okay, so let's see. Okay, so first of all, let's see. Let me give you an example. So how do we do this? Let's say I'm doing the example. It's in the, everyone see me writing now?
Yes.
Okay. All right. So I want to solve this differential equation. Now, whenever you have a differential equation with constant coefficients, we assume a solution of the form e to the m times x, right? Now, if I take the derivative, so what I'm going to do now is I'm going to substitute this into this differential equation. Okay, so this is going to be y prime n e to the mx. Now let me take y double prime is going to be equal to m squared, right? E to the mx, right? And now I'm going to substitute it. I'm going to substitute into this differential equation. So what I'm going to get now, I'm going to get m squared e I bought new lead. It's not from the dollar store. Minus, let's see, M E T N X. I'm just substituting it in. Minus 30 e to the mx, and that's equal to 0. Okay. All right. Now I could take the I could factor out this. Right, and this is not going to be equal to 0. Right, this is not. So therefore, this has, in order for me to satisfy this differential equation, this has to be equal to 0. Right, this can't be 0, so this has to be 0. So, and I can factor this. Right, I can factor this into what? Into m, then m squared. I could factor this. I can factor this into m minus 6, and let's see, it'll be n plus. It'll be n plus 5. All right. All right. n minus 6 and n plus 5. Right. When I factor this, so like I said, to solve differential equations with constant coefficients, you need to know how to factor, and we need to know the quadratic equation, because sometimes you may not be able to factor this. Okay. So so this is telling me that m is equal to 6 and m is equal to minus 5. Okay. So so now what? Well, the solution to my differential equation is y is equal to it's actually going to be c1. I didn't put a c in here because c1 6m x, no, self m. It's going to be 6x. Be 6x plus c2 e to the minus 5x, right? So in other words, my y1, to go what we had before, my y1 is e to the 6x, doesn't matter which one you call 1, and my y2 is e to the minus 5x. Both of these will satisfy this differential equation, right? And okay, so then any linear combination, this linear combination is a solution. Any c1 times 6x plus c2 times e to the minus 5x is going to satisfy this differential equation. That's what I have in my notes, right? So this is the general solution. I think in my notes I got, let's see, I'm looking at my notes. I got this, yeah, I got the, but it doesn't matter, right? In my notes I wrote it like this.
Excuse me, Professor.
Yes.
So I followed all of it up until where you factored it. I understand how you got m is equal to 6 and m is equal to negative 5.
Right.
But then now I'm questioning why you put in m is equal to 6 and m is equal to negative 5.
Remember now. Okay. Good. I could have made that clearer. Y, remember now, we started out with y is equal to m times x. So
Right.
I got two values for m, right? So the two values I got for m are 6 and minus 5.
Oh,
Right?
I see.
I'm assuming, good point, actually very good point. I'm assuming that this is going to be a solution. Okay. And you see, I end up getting two solutions. And if we had a third order, then you'd have to, so sometimes you can factor a third order. Okay.
Okay. Yeah, that makes sense.
All right. Good. So,
sorry. So
No.
I'm just making sure I understand this. So when you find the factors that makes the other side true, in this case equal to 0, you would then just substitute that m value back into the y, and then you would declare y1 is equal to like e6x is what you
Correct.
did, right? Okay,
Right.
gotcha. All right, thank you.
Now, let me just do it more general. Okay, that was an example, but let me do it more general. In other words, if we have, this is a differential equation with constant coefficients, right? Okay, that's a differential equation with constant coefficients. Now, I went through and did, and did this where I assumed the solution of this form, right? You could immediately, you don't have to do that. You could immediately write down what's called the auxiliary equation. In other words, let me put the auxiliary equation. The auxiliary equation is actually AM squared plus B, whatever the coefficients are, plus BM plus C is equal to 0. Okay. So you don't have to start out with this. So if I let me just do this for a second. If I go back to this original problem here, let me do this here. I can immediately write down the auxiliary equation. The auxiliary equation here is going to be m squared minus m minus 30 is equal to 0. That's my auxiliary equation, right? There's nothing, there's a 1 in front of here, there's a minus 1 in front of here, and there's a minus 30 in front of here. So this is my auxiliary equation. Okay, so you don't have to go through this. When you solve these problems, you don't have to go through this, all right? We could just immediately write down, I'm showing you why this comes about. We can immediately write down the auxiliary equation and then solve the auxiliary equation for m. All right. Now, some books use R. Okay. So going back to now, going back to this now. So m now, if we have a second order differential equation, right? To solve this, here's my auxiliary equation, right? This is just the quadratic equation. So m is equal to, remember the quadratic formula. So these are my values of m. Okay. Any questions so far? Make good progress.
Is that a quick question? For
Sure.
the problem, why didn't we solve when e to the mx was equal to 0?
Can you repeat the question again?
In the
Why?
previous problem. So you said it was m plus 6 and then n minus 6. And why didn't we also set e to the mx is equal to 0?
Well,
Short line, yeah, here.
yeah, here.
Yeah. So why didn't we also set the e to the mx to be also?
No. This can't be 0, right? So that's telling me this has to be 0.
Oh, okay.
I'm factoring this out, right? This has to be 0, right?
Okay.
If this is going to be a solution, then this can't be 0, right? So this has to be 0. So then, and the only way this could be 0 if that m is equal to 6 and m is equal to minus 5, then this could be 0. So that's going to give me my solution to the differential equation. That make sense?
Yeah.
Okay. So, all right. So, so when you have a second order linear differential equation with constant coefficients, homogeneous, that's what this is. It's a homogeneous second order differential equation with constant coefficients that I can immediately write down the auxiliary equation, and that's just going to be a times m squared plus b times m plus c, right? Where m is like x in the quadratic equation. And then my solutions to m is just given by the quadratic formula. Okay, so now we need to understand, though, that there are different cases. There are 3 different cases that we're going to come up against. See, it was nice that turned out in this problem here, we had 2 distinct roots, right? In other words, I had 6 and minus 5, 2 distinct roots. But what do we do? Gee, what do we do if I have 6 and 6, right? So there's something else that we're going to have to do. And what do I do if I have imaginary, right? It could turn out that that my solution to the when I go to solve this quadratic equation, right, this could be imaginary, right? The discriminant here could be imaginary. So there's going to be three different cases, right? We're going to have to look at three different cases. And case one is case one, and this is what I have in mind. We have distinct real roots, right? Distinct, that when we solve the quadratic equation, we get distinct real roots, okay? Case two is we have repeated roots, and I'll do an example of repeated roots. Repeated roots. And case three is where the roots turn out to be complex conjugate roots, or conjugate complex roots. I guess I'd rather say complex conjugate roots. So let's okay, so those are the three different cases, right? So what we just did was distinct real roots. So let's see what I got here. All right, so so here's how this works. So if we have I'll copy it again. Y double prime plus, and this is that, you know, we're going to have one root. All right, one root will be minus b and then, you know, another root would be with the minus sign. Right here I got the plus, here I get the minus. Everybody knows the quadratic formula, right? Okay. A little sloppy. All right, so what are the different cases? Well, case one, right, case one is that if b squared, right, if you take a look at b squared minus 4ac, this is what's called the discriminant, is greater than 0, right? If that's true, then you're going to get m1 and m2 are going to end up being different, right? So the roots, in this case here, the roots are real, right? The roots are real and they're distinct, right? The roots are real and they're distinct, right? Because if this is greater than 0, then, right, I'm going to get different values for m1 and m2. So I get two real roots that are distinct. But what if, now case 2, is case 1. So case 2, but what happens if this is equal to 0? Well, if this is equal to 0, right, this is 0 and this is 0, right, then m1 is going to be equal to m2, right? So this is, the roots are equal, right? We got roots are equal. And remember that when we have a second order differential equation, we need two independent solutions. So so in case 1, well, we got the roots as being real and distinct. In case 1, we get two linear independent solutions, right? These two solutions for the problem we just did, I just threw it out, are linear independent. But now when we have two the same, we don't have two independent solutions. All right. And then finally, case 3 is when this is greater than 0. Excuse me, when this is less than 0, when this is less than 0, then the roots m1 and m2 are going to be complex conjugates. The roots are complex conjugates. Okay. All right. Okay, so we're going to find that this is actually going to, that when we get, when the roots are complex conjugate, we're going to end up getting sines and cosines. When the roots are real, we're going to end up getting exponentials. And we're going to have to take a look at what do we do when we have two roots that are equal. We only get, if we have two, remember we have a second order differential equation, we need two solutions, and this is only giving us one. All right. So let me do let's just do some more examples. Let's see. Let me give you a second. Let me see if you can do this. See if you can solve this problem. I don't know if I'm going to get to case. I think I'll get to case 2 today, and then I'll get to case 3. It shouldn't take long at all. Like I said, these are simpler to solve than equations we solved previously. All right, I'm going to solve this because it shouldn't take long at all. First of all, I have to, so I can immediately write down that this is m squared plus 3m plus 2 equals 0, right? There's a 1 in front of here, so this is an m squared. I got a 3 in front of here. This is m, and this is 2. I can factor this. I can factor this into what? This factors into m plus 1 and m plus 2, right? Is equal to 0, right? I don't need to do all of this. You know, I just can immediately write down the auxiliary equation. So this is m is equal to -1 and m is equal to -2, right? So my solution is y is equal to c1 e to the minus x plus c2 e to the minus 2x. All right? So that's the solution to this differential equation. Not hard, right? Like I said, some of these are easier to do than other differential equations that we did. Okay. All right. Let me do the next problem now. I don't know if we're going to get. So why don't you? Hopefully everybody got that. But let me give you a minute now to try to do this one. What happens when you do this one? Try to do that one. Let me give you a minute to try to do that one without looking at my notes. All right, let me go ahead. So in this case here, just to get practice, I can immediately say that this is m squared plus 10n, right, plus 25 is equal to 0. Okay. And all right, so this is factorable into m plus 5, and m plus 5 equals 0, right? So this is m is equal to minus 5, and m is equal to minus 5. So now in this case here, I only get one solution. I get e to the minus 5x, okay? Well, I guess I should put a constant there too. Well, this would be a fundamental, e to the 5x is a fundamental solution, and a more general would be c1 times e to the 5x, right? So we need another solution, right? So we need another solution. Well, it turns out that the other solution, and I guess I'll spend the time and show you. But the second solution, so if we have repeated roots, it's as simple as this. It's as simple as this. If you have repeated roots, the second solution, right, is just going to be C2 x e to the minus 5x, all right? So that's going to be the rule that I think it's easy if I tell you what it is right up front, but I'm going to show you that that does work, all right? So once again, if we have distinct roots, I get my two linear dependent solutions, okay? If I have repeated roots, okay, I'm only going to get one solution, right? Like here, I only got the one solution, minus 5x, but a second solution is just going to be C2x e to the minus 5x. So you're just going to multiply by x to get your second solution. Now I'm going to prove to you that I'm going to show you that that works. All right. I'm going to show you that that works. If we go back to the well, let's see. Yeah. So I'll show you that it's always going to be the case, but I'm going to show it to you that it works. All right. So that's my y2. All right. So let's first take the derivative of this. Let's see. I got to use the product rule, right? So maybe C2. I could have left out the C2s. Let's see, C2. Yeah, and then this is going to be 5x, right? E to the minus 5x, right? Well, this is the derivative. Right? Just use the product rule here. Everybody's good up to this? All right, now I'm going to take second derivative. Well, this here now, this is going to give me a minus 5 C2 e to the minus 5x, right? And then I'm going to get a minus, not a minus. Let's see, if I take, yeah, so this is going to be, yeah, this would be a minus sign here. Nobody caught that? This should be a minus sign. Right? So now I get minus C2 5 e to the minus 5x, and then plus C2, then there's going to be 25 x e to the minus 5x, right? Is that right? Yeah, I made a mistake, right? This is going to be minus 5x, right? When you take the derivative, this is minus 5x. And so, so you take the derivative of this brings down to minus 5, you get that. Now here I use the product rule. So here x is just equal to 1. Then this makes this, here I got the minus sign. When I bring down this minus sign, makes this a plus, so I end up with that. Okay. All right. So now I'm going to plug it in. Now my differential equation that I had was this. Right. So all I'm going to do is I'm going to plug this into here. Right. I'm going to plug this into here. So I'm going to get, let's see, I'm going to get minus C25. I want to put the right e to the minus 5x, right? Minus, I'm just copying this. Right, that's x double prime. Okay, then I got plus 10. Now, my y prime is this. And then I got plus 25. Plus 25, and that's going to be C2x. This whole thing better equal 0. All right, so let's see. The whole thing equals 0. Okay, so let's see. So this, when I multiply this times this, I'm going to get 50. Okay, yeah, it does. Equals 0, right? Does everyone see that that I got 0 on this side? Because here I got a minus. This is and this. When you multiply this times this, right? I'm going to get, this is plus, I got a, well, let me do this. I got a minus 10 C2 e to the minus 10x. Then here I got a plus 10 C2 e to the minus 5x, right? So that they go away. And here, okay, so here times here, well, here I got a plus C2 25x e to the minus 5x. And here I got, when I multiply this times this, I got a minus C2 50x e to the minus 5x. And this times this gives me a plus 25x C2 e to the minus 5x. And so here I got, so these cancel, right? And then here I got a 25x e to the minus 5x. Here I got 25, and this is a 50. So I get 0 is equal to 0. All right. So I'm just showing you, you don't need to do this every time you do a problem. It's all you need to do when you do a problem is just multiply by x, right? Okay, so where are we? So let's see if you could do a problem. Hopefully everybody's finding this. Try this. And it shouldn't take long at all. What are the two solutions to this differential equation? Okay, so this shouldn't take long. Let's see. So immediately, right? I don't have to go through the x. Could if you want, but right. That's my auxiliary equation, right? Everybody understands, that's right. Got m squared. I got a 2m here plus 1. So that's my auxiliary equation. So now I could factor this into this factors into m plus 1, and m plus 1 is equal to 0. So I'm getting repeated roots. N is equal to m is equal to minus 1, right? And here n is equal to minus 1. So I got repeated roots. So my solution is simply C1 e to the minus x plus C2 x e to the minus x. That's it. That's the solution. Piece of cake, right? Am I right? Okay. Let's, I don't know if I should start with, let's maybe do one more problem. All right. Let me give you another one to try. And I hope you're trying to do these without looking at my notes. And let's put in the boundary conditions. So try to do this without looking at my notes. Let's try to solve this initial value problem. So this is once again, this is a second order differential equation. It's a homogeneous second order differential equation. We will get to the non-homogeneous this week too. All right, to see if you can solve this. This is going to take a little bit longer. I think this is the last thing we'll do today. Yeah, it's 12:19. And I'll do the complex conjugate case tomorrow. Or I'll give you another minute because I want to be able to finish it and give you the opportunity to raise questions. Now, previously we solved first order differential equations. Now we're solving second order differential equations. So for initial value problems, you can have two initial conditions. All right, let me go ahead and solve this problem. Okay, hopefully everybody could. All right, so I can immediately write down the auxiliary equation, right? The auxiliary equation is going to be equal to m squared minus 4m, right, minus 5 is equal to 0, right? Everybody's got that. So this is m. I can factor this into m minus 5, right? And m plus 1 is equal to 0. So in this case here, m is equal to 5 and m is equal to minus 1. So my solutions are y is equal to c1 e to the 5x or 5t. I guess I made it t. 5t. You can use t or x. Plus c2 e to the minus t. Okay. All right. So, all right. So that's my. So this is my general solution. Right. So now I want to apply the initial conditions. Right. So first of all, let's see. So it's we're told that when y1, when t is equal to 1, I'm using t here as the independent variable, that this is 0. So this is going to be 0 is equal to c1 e to the 5th, right? So e to the 5th plus c2 e to the minus 1, right? Right. So using this initial condition, I get this equation, right? Now I have to use the other initial condition. So I need to take the derivative of this, right? So let me take the derivative. I'll put this here. I'll take the derivative. This is going to be 5c1 e to the 5t minus c2, right? E to the minus t, right? When I take the derivatives, you bring down a minus sign here. Okay, good. All right. So I get this equation, right? Using this initial condition up here. So now let's see. So now this is going to tell me that 7 is going to be equal to 5c1, and I'm putting 1 in here again. So this is e minus c2 e to the minus 1, right? So I have two equations with two unknowns,
Is
right?
this e to the 5th? 5c1 e to the 5th?
No, this is oh, you're talking about right there. Very good, thank you. That's right. Yeah, I forgot the 5. All right, so all right, so now we got two equations with two unknowns. I think the best way to do this is to add these two equations. When I add these two equations, right, this cancels. So I'm left with 7. Left with 7 is equal to 5. Let's see, how should I write this? 5c1 Now, let's see. Well, now let me just write it like this. This is going to be equal to 6, right? Right? I can just say this is 6 C1 e to the 5th, right? Okay. So this is telling me that 7/6, and that'll be e to the minus 5, right? E to the minus 5.
Could you paper?
What's that? Do you have a question? I'm adding these two together, so I'm getting this. Okay, so this is telling me that C1, right? Is there an issue with my page?
Yeah, can you slide it up? Yeah, there we go.
Okay. So this is telling me that C1, this is going to be e to the minus 5, right? That's C1, right? This is clear? This is 6. This is C1, right? So I bring the 6 over here, right? Put the 6 down, yeah, divide everything through by 6, then divide everything through by, so when I bring this over here, this becomes, okay, this becomes e to the minus 5, right? So that's what my C1 is, okay? So now I got C1, let's get what C2 is, right? What's the best way to get C2? Let's see, so I can now use the equation that, I can put that in here, right? I can put my C1 in here. I think that's what I did in my notes. So this is going to be 0 is equal to 7. And then this is, yeah, so this ends up being, okay, right. So, and here I got to e to the 5th. Let me put it in. So this becomes, right? So this becomes, I don't know if I did it the same way. So then this is telling me that there's a plus sign here, right? So this is telling me that C2, I can write it like this, e to minus 1 is equal to minus 7/5. So this is C2 is equal to minus 7/5 e, right? Is that what I have in my notes? Yeah. Okay, so that's it. E or e to the 1. So, all right, so now I got my C, that's my C2, that's my C1. So my final answer would be y is equal to 7/6 e to the minus 5.
Excuse me, Professor.
Yes.
Your C1 is 7/6. Why is it 5 now?
Oh, that's this one here.
Yeah.
Oh,
Is that a 5 or a 6? Because it looks like a 5.
Yeah, you're right. Thank you. How did I get this? How did I get a 5 out of that?
Okay.
Yeah, here I put the 5 down. I don't know why I put the 5 down. I copied 5 instead of 6. Okay, good. Okay, so all right, so there's different ways of writing this. So let's see. So here's my C1. Okay, so C1, okay, and then my C1. Oh, I didn't finish writing this. So the C1 is times e to the 5t minus 7/6. And then this is going to be e to the t, e to the minus 1. No, this is e to the minus t. And this is just e. This is just e, right? This is my C2, right? This is my C2. So this is just e, or I can write it as 1. guess I might have written it as 1. All right, you can actually leave it that way, but probably a better way to write it would be to, it's perfectly fine to leave it this way. If you had a problem like this on the WebAssign, it should accept this, but I think it looks a little bit neater if you write it like this. Let's see, and if I write this as E, I can even take the 5 out, and make this as T minus 1. I don't know if I did that in my notes. I didn't do that part in my notes. Minus E, and then this would be 1 minus T, right?
Excuse me, Professor.
Yeah.
Is there a reason why you changed from using X to T? Or
No.
no, it's okay.
There's no, you can think it turns out that a lot of the problems that we're going to be solving going ahead is going to be with T.
Okay.
It's going to be with time. No, XT doesn't matter. For some reason, I decided to use T in my notes, so I guess I'll continue. I continue with the T. All right, so let's see. So we got 1 minute left. If anybody has any questions, I'll stay on, and take a look at your exam and get back to me if you think I made an error. One of the things I was very pleased. I think this is the first time since I've been remote teaching that everybody submitted through Blackboard, and I was able to read everybody's exam. Okay, so that's good. It's the first time in every class so far. I normally get 1 or 2 students where they can't submit through Blackboard or I can't read their exam, but everybody was successful. All right, that's it for today.
Thank you, Professor.
Okay.
Thank you, Professor. Have a great day.
Okay. Have a good day.
Thank you so much, Professor.
Okay.
I have a question, Professor.
Sure.
Are we gonna have exam this week?
I'm actually thinking maybe not. I don't know for sure yet. I have to see what we cover. I hate to give an exam like 2 weeks in a row, but it's only a 6-week course, and we got